Okay, so we're going to be talking about sequences over the next couple of weeks, and that's just basically a list of numbers that form a pattern. And you've done this since you were in kindergarten. It's just going to get a little funkier. So how is this going to work? Well, take a look at what you see below, and the idea would be not only can you find the missing number, but then can you write a rule to go along with what you see. So we're just going to kind of do this in pieces. So look for patterns, as you go along, and this one's not too hard to spot, hopefully. It looks like there's a common difference where we're adding 8 each time. So we do know that the next term would be 29. All right. Whenever this happens, by the way, and you're adding or subtracting the same constant each time, this is said to be an arithmetic sequence. Okay? And an arithmetic sequence, what's cool about that is that there is a special formula that you can use to where if you wanted to find, let's say, the 100th term of this, and you didn't want to have to keep adding 8 forever and over to get there, you could use this following formula here. It is a sub n, I'll give you what all this notation means in just a second, equals a sub 1 plus d times n minus 1. Alright, so this looks like gibberish, but what you need to understand is that a sub n just represents the nth term. So basically it's saying like, hey, if you want to find a term, use this formula. The subscripts on the a's are going to tell you what term of the sequence to use. Now since that says a sub 1, I'm going to choose the -3 because this literally translates to like the first term. Okay, so a sub 1 would be here. The second term, this a5, this would be, a5 would be a sub 2, a sub 3, a sub 4, so on and so forth. So that's kind of how that works. All right, now the D stands for common difference. So the common difference is going to be whatever we're adding or subtracting each time as we go across. And the n is going to be your unknown. It's going to be like the x of your formula. You're only going to fill in for n if you're looking for a specific term. So if I wanted you to write a formula for this, I would probably say, what's the explicit formula? That's what they're called actually. Or I might say, what's the a sub n? And if I did that, that's the rule where you just plug all this junk in. So the first term of this one's -3. The common difference is it's adding 8 each time, right? Wasn't it adding 8? Yes. And then n minus 1. So I kind of like to clean this up. I would probably distribute the 8. Let's see. Let's combine like terms. So this, ladies and gents, would be the equation that goes with this first sequence. And like I said, what's cool about it is if I'm like, hey, find the 80th term, all you have to do to find the 80th term is to plug in an 80 for n. And then I don't have a calculator, but you could figure that one out. I could too if I really wanted to, but no. So that's how that works. All right, cool. So arithmetic sequence, adding or subtracting the same thing every time. This formula works. Plug it all in. N is whatever term of the sequence you want to find. So now let's move on to the next one and see if it is arithmetic as well. I'll give you a chance to look while I'm erasing. Okay, so are you adding or subtracting the same number each time? I think the answer is no. Instead, can you spot the pattern? Okay, so it looks like you're dividing by 2. Another way of thinking of dividing by 2, guys, is to think of it as multiplying by 1/2. That's going to be how you want to approach these because when we use a formula here in a second, you have to put in the multiplier. You don't put in what you're dividing by. You put in what you're multiplying by. Okay, so times 1/2, times 1/2, times 1/2. So if I multiply that by 1/2, I'd get 1/8, right? So that's the missing term. So what if I want, the 20th term? Well, there's got to be a formula, right? Just like the other one. There is, but it's a different formula. In fact, this is a different kind of sequence. These are called geometric sequences, all right? And when you run into one of these fellas, the formula is a sub n equals a sub 1. By the way, if you don't know what I'm saying sub as like subscript, right? A sub n, a sub 1, times r to the n minus 1 power. So same as before, this is just sort of what we're looking for. We're going to leave the n as a variable, and I'm only going to plug in for the a1 and the r. And yes, this formula works every single time it's geometric. So let's plug in our first term, which on this one was a 2. What's the rate here again? Oh yeah, our multiplier. The r stands for common rate, if you want to jot that down. Kind of like on the last one, the d was the common difference, right? So common rate is the multiplier. And then n minus 1. Oh my gosh, hold on a second. I got a crazy dog. Whew. Okay, guys, we're in the clear. We averted a elderly person walking down the street that my dog decided was a threat. Okay, back to the math. I forgot where I was. No, I didn't. Okay, so here's our formula. And this is what we would use to find like another term, right? So if somebody says find the 10th term, they're telling you to find a 10, a sub 10. So you would just plug in a 10. And once again, not going to do it because I don't have a calculator and that's going to get crazy. Just be careful here. Please, please, please do not multiply these together and call it a 1. I know some of you already did and you thought you were being sneaky and crafty and clever. Do not put these together. Why not? Because one of them has an exponent, yo, and that is not allowed. Okay, moving to the next one. So we have arithmetic, we have geometric, and honestly, y'all, that's it. That's all we're going to study. So if it doesn't fall into one of these two categories, it doesn't even have a special name. And that's what's going to happen down here, because I don't know if you've looked ahead yet, but what is happening, right? This is weird. 1 over 2, 2 over 5, 3 over 10. There doesn't seem to be a pattern with addition, subtraction, multiplication, or division. And so this doesn't have a special name. It's like it's neither arithmetic nor geometric. Now that doesn't mean that you get out of doing it, okay? All that it means is you still have to figure out the pattern. There she goes again. You still have to figure out. Charlie, enough. If any of you have suggestions on how to get my little dog from yapping at everything that walks by my house, please comment below. Thank you. All right, back to the problem. Oh, and we're going to have to come up with our own formula over here. All right, so let's just try to figure out the pattern. Sometimes it's easier to separate and think of the numerator as separate from the denominator. So I don't know if you've noticed, but look at your numerators. 1, 2, 3, 4, 5. So I'm guessing it's going to be a 6. All right, now the denominators are a little bit trickier. You might see it as that you're adding 3, then you're adding 5, then you're adding 7, then you're adding 9. Ooh, there's a trend there, right? So maybe the next one I just add 11, so it will be 37. All right, cool. So we could find that, but now how do we get a formula for all of that? Well, my recommendation is, like I said a second ago, view the numerator and the denominator as separate things. And what we're going to try to do is we're going to try to write an equation so that if we use n as our variable, whenever we plug in n, it's going to create one of these terms. Now I need to be a little bit more clear because what is n? You may have already caught on from above. But if you haven't, the n is what term it is. So like, see how this is in the first spot of the sequence? So that means that n is actually 1. This means that since it's in the second spot, this is when the n is 2. This is my third term. This is my fourth term. I highly recommend writing these numbers underneath because what you're trying to do, gang, is come up with a formula so that if you plug these numbers in, the 1, 2, 3, 4, 5, that it turns into the a sub n's, which are all of these numbers up here. So looking at my numerator, see how they match exactly? Well, since they match exactly, I know my numerator is just an n. Because if I plug in a 1 here, right here rather, it would give me the 1. If I plug in a 2, it gives me a 2, so on and so forth. The denominator is a little bit trickier. And when you see numbers, I always try to multiply first. If I see numbers growing steadily, I'll just try to multiply. But if I see numbers growing more and more each time, like this one, it grew by 3, but then 5, but then 7, so it's like increasing each time. Usually that's a trigger that there's an exponent involved. So if you're good at your exponents, this next part will make sense. But when I look at these numbers, 2, 5, 10, 17, and 26, I know my numbers so well that they feel really, really close to perfect squares, right? What are your perfect squares? Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, blah, 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 blah. You see what's happening here? These numbers in the denominator are only one more than all of the perfect squares out there. So why not try squaring in and then adding 1? I know that's hard, and it's going to take you some practice, but the better you know your number sets, like your squares, and maybe even know your cubes, right? Because sometimes we may be cubing things. So please know your cubes as well as your squares, and that's going to help you identify a pattern, okay? So are there any other number sets that might pop up and scare us to death? Well, of course there are. There's actually a set of numbers that you may not know called factorials, and you may know them. In fact, I think I've talked about them with most classes, but if not, here they are. A factorial is basically saying that you take that integer and you multiply it by every integer less than itself until you get down to the number 1. Okay, so 5 factorials, in other words, we'll start, actually I'm going to do 6. 6 factorials would be like 6 times 5 times 4 times 3 times 2 times 1, which is going to give you a nice 720. 5 factorials, same idea, 5 times 4 times 3 times 2 times 1, that's 120. 4 factorials, 4 times 3 times 2 times 1, 24. 3 factorials is 6, 2 factorials is 2, and 1 factorial is 1. And yes, 0 factorials is also 1. I know you thought I was going to say 0, but I didn't. So what do we do with this information? Well, you freaking memorize it is what you do, because if you can recognize these numbers in a pattern, it'll make things a lot quicker to do, like something like what I did up here. Okay, so what else do we need to know about factorials? Well, you might need to know how to simplify. So let's say it's like 13 factorials over 10 factorials times 2 factorials. Okay, well, to do this problem, this would be a heck of a lot of multiplication that you don't want to have to do by hand or in the calculator even. So what I recommend is kind of thinking of this as being expanded. So 13 factorials would be like 13 times 12 times 11 times 10 times 9, right? All the way down. And on the bottom, we have 10 times 9 times, oh wait, I'm going to stop. I don't know if you see it, but I want you guys to look up here. I was about to do 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 on the top, but look what I'm doing on the bottom right now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All of those are going to cross out, right? Because we're reducing this huge fraction, and they are like terms, so you can just cancel from top to bottom. Now, there's still a 2 factorial over here, so I do need to keep that, like a 2 times 1 for that one, okay? And then what I do is just look at what's left over. So I have a 13, 12, 11 over a 2 and a 1. Can I reduce any further? Why, yes, I can. 2 can go into itself once, and it can go into that 12 6 times. And now my final answer, kids, is 13 times 6 times 11. Like I said earlier, I don't have a calculator, but whatever that is my answer. And these are kind of fun to reduce once you get the hang of it. Okay, so what else? What else? Oh my gosh, there's one more thing. Okay, so what if you need to write a recursive formula? These are not that much fun. But they're not hard either. Okay, a recursive formula is different than the kind of formula we did above. Do you remember what that was called? That was called, I think I wrote it down up here, explicit. Oh, I erased it. Anyways, those are explicit whenever you do it, a formula in terms of n. A recursive formula is whenever you write a formula in terms of the first term and what happens to get the second term. I know that doesn't make sense. Also, bonus points for anyone who can actually decipher what I just wrote. Write formula in terms of the first term and what happens to get the second term. So here's what I mean by that. Let's go back up to this fella, the first one. What was that? Okay. I hope no one gets motion sick because you just threw up. All right. Plus, 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 beautiful, dot, dot, dot. Okay. So, okay, so what we're going to do is we're going to start with a recursive formula by telling our reader what the first term is. Okay? So a sub 1 is -3. And then what we do is we tell them like the pattern. So basically the pattern on this was adding 8. Remember? Add 8, add 8, add 8. Okay? So the way I explain it is I tell them, I say, okay, so the first term is -3. And so if you want to get the next term, all you have to do is take the current term and add 8 to it. Now, I just used an n because I had used so many n's above. I will say that most of the math world likes to use a k when they're using recursive formulas. And no, I don't know why. They just like that letter for this kind of formula. But when you see that subscript, don't wig out. K plus 1 just means like I'm looking ahead at the next term. When I use a of k, it just basically means like the term I have, or I'll call that the current term. And the only other subscript you might see is sometimes people like to write things as a of k minus 1, like this for instance. What I'm about to write is actually the same kind of thing. Some people like to write it like this. The current term is equal to the previous term. They're subtracting 1 to say go back a term, right? The previous term plus 8. These are synonymous, guys. You do you. I don't care which of these that you use, whichever one makes you feel better, but please don't forget that you need to give them the first term as well. Alright, so hopefully this helped you out and got you started so that you can either take a formula, take a sequence and write a formula with it. You can write it recursively or explicitly. You can also, hopefully, if I gave you any random formula, n plus 5 over 2 n squared, hopefully even if I gave you a formula and said, hey, list out the sequence, I hope you could do that too, right? That just means find the first term and the second term and the third and however many I want you to find. How would you do that? Well, you're working backwards, you know. I've given you the formula. So if you want the first term, that's when n is 1. So you just plug in a 1. 1 plus 5 over 2 times 1. N is 2, plug it in. 2 plus 5 over 2 times 2 squared. So just got to be careful with PEMDAS. But other than that, you'd clean these up and you'd be done. And this video is getting way too long. I hope that helped some of you. Good luck. Peace.